Okay, so we're moving on to more complicated statistics now, and we're going to look at the chi-squared test. There's two different ways you can use this. Today we're going to look at the more straightforward way, and next lesson we're going to look at the slightly more complicated way. Today's lesson is going to look at the chi-squared goodness of fit model. Basically, you need to imagine that you've gone out and you've collected some sample data, kind of like what you did when you went out at the beginning of the term and you collected data from various students. Obviously, you were collecting just data from some of the students. You didn't collect data from everyone around the school, so you collected a sample. The chi-squared goodness of fit model tells you whether or not your sample is close to your population data. So whether the sample that you took of the students around the school is actually representative of the school as a whole, for example. Or if you went out and you collected some data about the heights of, say, women, whether or not you're not going to look at every woman in the world, but you collect your sample and whether or not that sample is relatable, is close to the data that you would expect for the entire population. So we're going to look at this example and I'm going to go through with you how you carry out the chi-squared goodness of fit test, and then you're going to try it yourself. So the first thing is we need to look at what information we're being given. So a group of 256 teachers chosen at random are asked their star sign. What would you expect to see? Well, obviously there are 12 star signs, and you would expect, particularly with a sample as big as 256, that you would have an even spread of teachers through the star signs. So you'd have pretty much the same number of teachers in each row here. Because generally we don't expect our profession to be determined by our star sign. So let's have a look and see what we found out. So we asked these teachers, when you start your chi-squared test, you need to write two hypotheses, and this is always the case. The null hypothesis is that there is no difference from what you would expect. So your sample represents the population. The alternative hypothesis is that there is a difference from what you would expect, that your sample is not representative of the population. So the null hypothesis is saying no, there will be the same number of teachers in each star sign group. The alternative hypothesis is saying there's going to be a different number of teachers in some of the groups. So they are diverting from what we'd expect. They're not representative of the whole population. Because we would expect that the whole population on Earth should be evenly spread between all of the star signs. Okay, so the first thing we do is we collect our observed data, just like what you did when you went out and collected data from the students. So these were the answers given by the teachers. These were their star signs. So 29 teachers had the star sign Aries, and so on. We could ask the entire population of the world, and we'd expect that you should have exactly the same number of people, or as close to exactly the same number of people in each category. Okay, so now we're asking, does our sample here of 256 teachers, does it fit what we expect from the population? Have we got around about the same number of people in each group, in each category? So, the first thing we then do is calculate the expected number of teachers in each category. So we know we had 256 teachers. We know there are 12 categories that they can be split into. So we just divide 256 by 12. And so that gives us 21.333. So we'd expect there to be 21.333 people in each group. When you come to calculate chi-squareds, your expected value should always be greater than 5. So we can look at these now and we can see that there are some similarities. 21.33 is quite close to 22, very close to 21, quite close to 19 and 20, but there are some big differences as well. So let's go on and see whether or not statistically our observed values fit the population. So our next calculation is called the residual. It's basically looking at how far our observed data deviates from the expected data. So we do the observed value minus the expected value. So in this case 29 minus 21.333. Obviously you're going to get some negative numbers where your observed value is less than your expected value, and that's fine. We're going to deal with that in a minute. So this is called the residual. Once we've calculated that for all of our categories, we then square that number, and that gets rid of our negatives. So whatever number you have here, you square it. After that, you then divide whatever number you have here by the expected value again. So in this case, I've done 58.782889 divided by 21.33, and that's given me this value here. And then I add all of these up to give me my chi-squared statistic. Once we have our chi-squared statistic, looking at it, it doesn't mean very much. We need to use it for something. And so we use what's called a chi-squared table. So we take our sum of our components, this is the component column here, we take our sum and we go to this table. Now at the bottom here, I've put down the null hypothesis to remind us. The null hypothesis is that there is no difference from what we would expect. So that's saying that there is no difference in the observed number of teachers in each category. They are all pretty much the same. So we've got a few points on this table. You'll notice here we have the probability. And this is the probability that any deviations, any changes from normal are due to chance. So values up here of 0.99, that's actually 99%. So when you read the table, and we'll talk about how you do that in a minute, when you read the table, if you get a value of 0.99, there is a very, very high probability, a 99% probability, that any differences in your data are purely due to chance, that there's no actual difference between your sample and the population. We also have these things here, the degrees of freedom. Now the degrees of freedom you calculate by doing the number of categories minus 1. So in this case we've got our 12 star signs, 12 minus 1. So we're going to be looking at this value, or this row here. Anything that is in these last two columns here means that we can reject our null hypothesis. Now what this means is if you get a value in one of these two columns here, the probability, that differences in your data between the sample and the population, the probability that they are due to chance alone is very low, 5% and 1%. So any of those differences between the sample that you've collected and what you'd expect from the population must be due to something else. There must be a significant difference between your sample and the population. So let's have a look for our star sign. Let's have a look at our teacher's star signs. We got the chi-squared statistic of about 5.09. So we go to our table here, and we know that we are looking at 11 degrees of freedom, and so we follow across until we get to 5.09, or the closest number to 5.09, and that's going to be between these two values here. So what this tells us is that there is between a 90 and 95% probability, so the numbers are up here, 90 to 95% probability, that the differences between our sample data and our population data are just due to chance. You just happened to pick people who were mostly Aries. There's nothing special about teachers. Teachers aren't necessarily all Aries. Had we got a chi-squared value that was down here between 19.68 and 24.72, then we would be able to say actually there is a significant difference between our sample data and the population. There must be something about being a teacher that appeals specifically to people who are Aries. But we didn't. We're down here. So we say that we accept the null hypothesis, and there's no difference between our sample and the population. Okay, so this is your turn now. So we've got a company produces stickers for a children's magazine, and it claims that 60% are regular, 30% are rare, and 5% are shinies. So a sample is taken of 100 stickers. This is important because think about what percent means. 100 stickers. And it contains 45 regular stickers, 50 rare stickers, and 10 shinies. So I want you to work out whether or not the sample fits the claim of the company. The first two things you need to write are your null hypothesis and your alternative hypothesis. You're then going to set up tables exactly the way that I've shown you, and you're going to work through calculating your expected values, although not a lot of calculation is needed because look, here are your expected values. Calculating your residual squared, your component, and then the sum of your components to give you your chi-squared value. Then flick back and use the table. Don't forget to work out what your degrees of freedom are, and read the table to find out how well the sample fits the claim of the company.